guys are engineer, okay? I'm not running a arithmetic class that square root of 64 is 8, you give me the answer. That is the obvious answer, right? But tell me whether is that correct or not. What is the advantage of having m is equal to 8 when n is equal to 64 as opposed to something else? I'll give you 3 minutes to discuss that. Who wants to take the lead? Did you understand what I'm telling? If n is equal to 64, what should be the value of n according to that differential calculus? What he suggested? 8, correct? Square root of 64 is 8, correct? Am I correct? Square root of 8 is square root of 64 is 8, right?
Yes.
So shall I take the ripple carry adder 8-bit wide? How many of you are in favor of that? Just go by the pure maths. N is equal to 8 when n is equal to 64. I want to see, raise your hands. Like this. 1, 2, 3, 4, 5. Okay, 5 hands I see. What about n is less than 8? How many hands are there? M is less than 8. Nobody? M is larger than 8. Come on, guys. Give me an answer. What do you think? What should be the value of n? Yes? Loudly so that everybody can hear. What's that? Larger than 8 in between, and then first and last stage is smaller. Okay, I can see what you're thinking. Okay, that's a reasonable answer. What about you? Yeah. Huh?
Makes sense.
What she says makes sense, right? Okay. Any other different recommendation? What's your recommendation?
I don't know. I tried different values. Simulation.
In a way, you are correct. Okay. The decision is not very straightforward. You just do some differential calculus and then say m is equal to square root of n. It does not involve so many other intrinsic design requirements. What are the intrinsic design requirements? You will do simulation, and I'm with you. But what is the reason why? What you're looking for doing simulation?
Well, I'd imagine you'd look for the lowest worst case delay, because this would be like the determiner, or the likely determiner of your overall clock speed.
Yeah, I mean, without further suspense, I want to bring it to you. This one. See, at the input of each multiplexer, you have to, of course, this comes from the setup unit. You have to have an AND here, right? You have to AND P0, P1, P2, P3. Now, if you have 8-bit RCA, then it becomes an 8-bit AND operation, correct? So much of the delay will be eaten up there. So what is the point you're trying to save delay by of the AND or gate there? So you need to think in a very holistic way. Now, one way to implement this function is to use cascade like this. These are called cascades. And you invert it at the end so that it goes, because the signal value reduces subsequently because of the RC delay. So to restore the signal, you use an AND gate. So this could be a way to implement this function over here. Okay. The main problem is that if I have to use n is equal to 8, then I need an 8 input AND gate, which will be very slow. So to justify your decision to do simulation is the right, because you'll have to do the simulation, but you have to know what you're simulating. What you're simulating is that how can I make this delay smaller than the delay associated with the AND or gate over here, because the carry propagation takes place this. So you need to do simultaneously, see that which gives you the better result. Because it's not just the 1 unit of delay, like this type of multiplexer implementation, but the selection beat over here will be also responsible. Correct?
But that's not on the critical path.
Very good.
So,
He says that that's not on the critical path. Do you understand what he's telling? How many of you agree with what he just now said? What? Yes. What is that?
that's right.
What he is telling is that, hey, look, P0, P1, P2, P3 is generated above, right? That's generated, and then this starts thing, right? So why are you bothered about the time it takes to decode? I mean, to set the select value, correct?
Yeah.
Do you understand what I'm telling? But if you are really designing a fast adder, then you must understand that if you have a string of 8 NMOS gates, you will come to that later, you'll find out that the delay of that may actually cause some problems in terms of the propagation, the critical path. Do you understand my point? You see, these bits may be generated at the top, but then there is a signal propagation through 8 different stages, correct? So that is now competing with those. Do you see that?
Okay, so it's two.
So it's not clear.
Okay.
If you look at this, you say that, okay, P0, P1, P2, P3 has been generated earlier, so I'm not bothered about that, that's not the critical path. But the construction of this is now competing with the critical path. Is it clear? So that's why engineering job is very, 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 very difficult. You have to understand everything and then do the simulation and then select the right way to do it. How many of you are with me? Does this make sense? So do not, my point is that do not just, pick up a textbook or pick up some slide and say that, okay, that's the answer. You have to make effort to understand every aspect of the design engineering. Yes?
Is there a name for that chain that this chain right here?
Pardon?
Is there a name for this?
Is there what?
For this carry-out generation circuit?
Uh-huh.
Is there a name for it?
Oh, this one?
Yeah.
I mean, this is, I just took an example to show that how these things are implemented, often by baskets and all.
Yeah.
Typically, for Manchester carry adder and all, they use this kind of thing.
Okay.
But I don't want to really throw in lots of terminologies and lots of different things.
Okay.
I'm just giving you the example that a 4-input or 8-input NAND gate or AND gate, you don't have to do by the way the static CMOS we designed, right? There are some faster ways.
So also essentially you're saying that if your bit size per stage is high enough, your skip logic will take longer than, could potentially take longer than your ripple carry, right?
I mean, for all practical purposes, it may not be as bad. It may still be dominated over here, but then that's where you need to do the simulation and you need to do very accurate, because this also depends on the layout, right? Because we are not talking about the ideal case now on the paper, but once you do the simulation, then the layout and everything comes into play. Okay, so if do you have any other questions on carry bypass adder? If you don't have, then we'll move over to the. All of you understand this? Any question? Do I need to go through it again? How many of you want me to go through it again? No one.